Yeah, perfect. Thank you. So today's topic is on inline quality assurance of sediment detection using thermal effusivity sensors. We have with us today. We're going to have Dr. Mies from bdtronic. bdtronic is one of the leading companies in the technology space of dispensing different 2K adhesives, potting compounds. They have a very impressive portfolio of process machinery to help automate and scale production processes, in particular for industries like electric vehicles and manufacturing battery packs and these types of products. Now, Dr. Mies has graduated with a PhD in chemistry with a focus in elemental organics from the University of Würzburg in 2014. He is a European adhesive engineer, 2023 from IFM in Germany. Joined bdtronic in 2015, originally in project management and engineering of dispensing machines. In 2018, he moved into a process development for adhesive role. I've had the great pleasure to get to know Jan over the last 3 or 4 years. I knew him by reputation before then as an authority, as a leading expert in this field of application. Yeah, very, very grateful for the opportunity to collaborate with Jan and his team. We also have Till Schulte, who joins us from HELLA Forvia. HELLA is one of the world's largest tier 1 manufacturers, focusing a lot in electronics, headlamps, different components. I think they're the 7th largest in the world. Till has been a wonderful collaboration partner on this, actually bringing us into the manufacturing environment. And we're so excited to be able to finally share data with you today from that collaboration. Till is a process expert in production, a process engineer, particularly focused on polymer technologies. He's the global technology network coordinator for polymers within Forvia HELLA. Also, well known in the industry for his reputation and domain expertise in this area. And these fine gentlemen are going to be joined by one of our leaders here at C-Therm, our VP of Engineering, Brandon Brown. Brandon first graduated from Queen's University, one of Canada's top engineering schools, with a degree in applied sciences. He's more recently gone on to, he's just about to complete his PhD in electrical engineering from the University of New Brunswick. The University of New Brunswick is where our technology originally spun out of, and there's a really interesting history here in applying it in different process monitoring type of applications. So really excited to be able to welcome these fine gentlemen. I'll provide a little bit of background on who C-Therm Technologies is. I think looking at the registrations, a lot of you know maybe who we are, but there's some newer faces that may be less familiar with us. So our raison d'etre in life, our reason for being, is all about measuring thermal conductivity. We're experts in measuring thermal conductivity. We're a top leader in the field in transient methods for measurement. Transient because they're fast, they're very versatile in terms of sample format, and they lend themselves well to both accelerating R&D in research labs, but also the ability to migrate them into production environments, as we're going to talk a little bit about today. So this is a really interesting example of taking something measured in the lab, and Brandon will talk a little bit about how some of our tools are applied first in formulation development, but the value of bringing them into manufacturing environments for quality assurance and real-time control. So the Trident pictured here is our product that is most popular, and if you know C-Therm, you probably know Trident. It offers the benefit of bringing multiple transient methods together under one platform. When it comes to thermal conductivity, you've got a broad variety of different sample formats. You really need more of a toolbox orthodox approach in measuring the thermal conductivity. If you're interested in Trident, if you are more on the formulation development side and would like to learn more about that, that's not the focus of today's presentation. But of course, there are a lot of resources that we can share with you, and we'd be happy to set up a call individually if you would like. Just maybe enter in the chat box if that's something that you would be interested in. Want to just offer a little bit of perspective of some of the clients we work with. It's a broad range from Intel, 3M, all kinds of different groups in polymers. Covestro here is a good example. And this is one of the testimonials available on our website. There's a list. Thank you, Angad. Angad Lumba, a quick shout out to Angad, is helping us run this event. You'll see him pop up in moderating some of the chat. A quick comment from Jose Fonseca, a researcher at Covestro, just on the C-Therm product provided to their group, provides a fast, accurate capability to measure the thermal conductivity of our polymers with C-Therm's patented high-precision MTPS sensor. This is the exact same type of sensor that we're going to be featuring in the inline monitoring work that we're going to be presenting shortly. So we're going to use two thermophysical terms here somewhat interchangeably throughout this presentation. And I do just want to take an opportunity to distinguish the two. I think thermal conductivity, most people are familiar with. Looking at this audience, I would suggest most of us understand what thermal conductivity is as a fundamental heat transfer property of material and how important that is in different applications in EVs around thermal management. Wherever you have thermal management, you typically have to have a good understanding of the effective thermal conductivity of your composites and materials used. But thermal effusivity is the other thing that these MTPS sensors measure, and is more typically what we use and focus on in manufacturing, where it is the square root of the thermal conductivity, density, and heat capacity. So in terms of looking for variation in a material as it's undergoing processing conditions and wanting to make sure that it's in a consistent state of manufacturing, that it's homogeneous, and that we're getting the same quality of material today as we did last night on the shift before and a month ago, or in a different facility on the other side of the world. Effusivity is a really great thermophysical property to have a look at that consistency. And it directly, of course, incorporates thermal conductivity, which is a critical performance attribute of the type of materials we're dispensing, whether that's a TIM or other polymers and so forth. So effusivity is something you're going to hear more and more about as we progress. It is sensitive to the composition. So when we talk about fillers, this is going to have a very significant effect in terms of the dispersion or distribution of the filler in the material. It's sensitive if you're looking at powders to the crystallinity, to the morphology, to the shape and size of these things, the densification of the material. All of these things work together in terms of influencing the effective effusivity of the material. So this is one of the reasons that we like it in a lot of different process monitoring applications. Just one quick example from some work done in the past, a slightly different field. This is work sampled from a publication with GK and Hoganese, blending metal injection feedstocks. So this is a powder material that uses a polymer and metal. The polymer is used as a binder, but the distribution of that and the homogeneity of it is very important. You can see our sensors mounted on the lids of the double cone blender. If you're interested in this work, there's a link in the chat to it, but it's just another example of taking these sensors from a lab environment and putting them and deploying them in manufacturing environments. So these sensors were originally developed, in fact, for process monitoring application, the MTPS sensors. Brandon's going to detail how those work and what they look like a little bit further in his section. But I just wanted to put a reference to some of the previous work we're building on here year over year. This work presented by the team at GK and Hoganese and some of the research staff at C-Therm. So I really want to transition now more into the current scope, this collaboration, but I wanted to provide a little bit of context to how it started. So this collaboration really started about 4 years ago. C-Therm Technologies is an expert in sensors, in thermal conductivity measurement, and has applications ranging from lab environments to process monitoring. bdtronic, as I introduced earlier, is an expert in the machinery for dispensing these types of materials in production environments. Their list of EV manufacturers using their equipment is a who's who list of the major, I would say, industry players in that space. Very, very impressive technology, very, very high quality. We knew that when we were looking to explore this space, we wanted to work with a really reputable group that had a very strong reputation and significant technology in their dispensing equipment. And that really attracted us to bdtronic, and in particular, the opportunity to work with Dr. Jan Mies. And then Jan's team introduced Till's group, Forvia HELLA, which is, as I mentioned earlier, one of the largest tier one manufacturers in the world. And Till brings a tremendous domain expertise in his own right to this area. And so this has really created a strong collaboration group that we've advanced significantly through multiple trials and some iteration that you're going to learn more about in the scope of today's presentation. So the motivation for all of this really stems from the work that we're also doing in formulation development. When we work with clients in formulation development, Emma, we've got a pop up there. When we work with clients in formulation development, one of the biggest issues we face is the dispersion of fillers, whether it's boron nitride or other filler materials. Okay, it must be on. Sorry, folks. But there's a couple of challenges in this. One is getting the dispersion and then maintaining it. And this is the most critical aspect to achieving a higher thermal conductivity. A lot of these materials we work with, they have some stability aspects to them. Their shelf stability ranges considerably depending on the formulation, the volume, the dispensing conditions, the transport conditions. There are things that are within our control as manufacturers, whether you're the chemical manufacturer or the OEM trying to put this together. And there are things that fall outside of that control. But this is a known industry and this known issue in the industry that you can see a couple of different things happen. One is you can get sedimentation, or two, you can get agglomeration. And both work against us in terms of producing a high quality product where we want to achieve an optimal, high thermal conductivity, which promotes better thermal management, which promotes better performance, safety, and et cetera in an EV. So this was the motivation for us and speaks a little bit to the work that we're going to introduce. So I've taken up more time than intended on the intro. I get excited about this stuff. There's a lot we want to share, but I'm going to pass this over now to my colleague, Till, who's going to join us on camera. And Till, I'll ask you to take it from here.
Thank you very much, Adam. Hello, everybody. So just to start and get a bit deeper into the polymer technologies, I would like to start with the usage of polymer materials in automotive electronics. So it's mainly categorized in 3 sections. Besides, there are some special application where we will get a bit deeper in. So we start with bonding or sealing. So it's structural gluing for components, as well as a vibration dampage of big components on PCB, for example, as well as sealing of housings or connector for encapsulation of electronics. Common materials are here normally pasty silicons, epoxide, acrylates. This depends mostly on the requirements and test specification. The second one is the potting and encapsulation. So it's normally used as humidity and dust protection. Often, if a complete seal device is not possible due to any kind of reasons, um, and it's as well a protective or protection against aggressive mediums like transmission fluids, for example. There, more low viscous silicones are used, and as well as the polyurethanes or epoxides. And this depends on the, how to say, a medium. So what medium is used and how the requirements there are. The third one, or the third category, is the conformal coating. This is typically used for humidity protection and electromigration protection, as well as dust or particle protection of fine pitch components. So means, component joints which are really close together, where it's really narrow space and a small particle could lead into a failure. Their common materials are acrylates and silicons, and there's a newer group available. These are the synthetic rubbers. Beside that, we have some special application, for example, a chip underfilling. So this is normally used if the chip has to be coated afterwards to do not have any kind of climate conditions under the chip. We have the optical bonding, for example. So this is often used for displays just to ensure there's no air between the screen and the LED display or LCD display. Then we have electrical conductive gluings and thermoconductive gluings. And besides that, the most rising materials in the past years are the thermal interface material, which are used to transfer heat out of components. And on the next slide, we could go a bit deeper into that materials. So what are thermal interface materials for? They are mainly used to transfer heat out of a heat source into any kind of heat sink. And in electronics, a normal stack, you could see it in the middle, is that you have the components soldered on a PCB, and the PCB is normally screwed or rivet to a kind of heat sink. The second one is the topside cooling. You could see it's below. So in this case, the PCB is tilted, so the component is directly facing to the heat sink, and the heat transfer does not has to be performed through the PCB material. In both cases, you see, and this is a smaller picture on the right, even if you have a good tolerance chain, even if you have good surface conditions, you will have only small physical contact points between your PCB or your component and the heatsink. Most of this will be air, and the gap fill materials or TIM materials are used to really close this air gap between a heatsink and the heat source. These materials have, due to the formulation, some negative aspects. Normally, they're known to be highly abrasive, they are pressure sensitive, and they tend to settle down, so sediment over time, which could lead to significant application issues like downtimes or higher scrap, as well as even higher wear and tear of your entire dosing system. The material consistency and homogeneity is crucial to really perform a stable production, as well as a reliable thermal management of the produced part, for sure. The inline monitoring of the material characteristics, especially the thermal conductivity, and perhaps as well kind of settlement detection, is a good opportunity to really measure the behavior of the material inside the material pipes, the tubes, the pumps. But for sure, any sensoring solution needs to survive this challenging condition. To go a bit deeper into this materials, Dr. Mies will now go into the mechanical and chemical properties of these materials, as well as the processing of these materials. So he will introduce you into dosing of these materials.
Today I want to bring you a short introduction to such spoilage pathways when it comes to automatic adhesives.
Jan, sorry to interrupt. We're just having a little bit of difficulty with, I think, the mic. Let's just take a moment to troubleshoot that. We had it, of course, it was working perfectly when we did the warm up, but can you speak again?
Again?
Okay. Maybe we switch from your headset, or
Let me check.
Test 1, 2, 3.
1, 2, 1, 2.
Much better, my friend. Okay, perfect. Please continue.
Okay, so let's jump right in. Okay, sorry for the inconvenience. So to make it brief, we want to talk about spoilage pathways in adhesive applications. And so on the next slide, I bring you a brief introduction in how does an automatic dispensing equipment could look like. And I divided it into two sections. That is, on the left-hand side, you can see an application system for non-self-leveling materials. Here you can see it's a system where we pump the material directly out of the container into a hosing system, which feeds the material directly into a dispensing setup with a static mixing head. And on the right-hand side, you see a typical material preparation system for self-leveling materials. It looks a bit different because their rheological properties differ a lot from the non-self-leveling materials, which requires, of course, a different application setup. Those materials, they have to be agitated. They have to be recirculated. I will come back to that specific topic later in my talk. But to understand what kind of spoilage mechanisms we have to divide the materials not into chemical classes, but into their rheological patterns. That means how is their viscosity. So on the next slide, please. You can see this is a brief introduction in those self-leveling materials. I think Till already presented some applications there. The viscosities, they lie in between 5,000 and 60,000 millipascal seconds. They are designed for applications for PCB encapsulation, for dam and fill process. I think Till mentioned that as well. Potting of inverters or battery cells. And they are designed for an ideal flow inside the part, but they bring some aspects with their flowability that is the tendency for sedimentation. So normally those materials they are made out of a polymer and filler particles, and since the viscosity is so low, the filler particles have a tendency to sediment, not only in the original containers from your supplier, but also in the automatic dispensing equipment. On the next slide, I highlight a little bit the highly filled thermal interface materials, which are made for heat management of electronics. I think Till presented a nice slide how those materials do their job on the electronics part itself. As you can see, the viscosities are much higher than with the self-leveling materials, typically between 250,000 and 800,000 millipascal seconds. They are normally engineered for thermal management in electronics, PCB assemblies, and of course, which is more or less a newer field, battery systems for heat management. cars and other mobile applications. The main feature of those materials that they are really, really highly filled. I will highlight that a bit because later in my lecture we will go into into a deeper understanding of what consequences come along with that very high filler content. Especially the challenges in production lines are the differing handling characteristics, the reduced flowability. I mean, as you can see on the picture, we are talking about pastes. Yeah, they don't have a real tendency to flow, and that makes them, of course, in some aspects, a challenge in automatic production. On the next slide, we jump right in to the first spoilage mechanism, which is typical for low viscosity materials, which I showed you on my second slide. A typical phenomenon is sedimentation. So the material has a low viscosity, and the materials, they tend to sediment not only in the original container, but also in the automatic equipment. This example, as you can see here, is a typical phenomenon that when you have a low vector of speed inside a hosing or a piping system, those filler particles, they tend to sediment in the hosing and piping. And it's like a three-step way into madness, I would say. First, it starts to sediment in areas with low vector of speed. And those aggregates, they tend to build up until they reach a certain level of thickness. And then in the second step, such particles, such aggregates can start getting mobilized again, and then get transferred and transported through the hosing and piping of such a dispensing equipment into areas with a narrow diameter, such what could be like a nozzle or a valve. And when such a particle is moved into such a position, it could block the system and could cause a downtime in the equipment. You can really describe it similarly to getting a heart attack or getting a stroke in biological environments. That such kind of an aggregate or a plug gets mobilized and gets transported to a critical area and then is blocking everything. On the next slide, I will focus a little bit more about the characteristics that when you lose filler content somewhere in the equipment, not only can this mean that you get a downtime in the equipment, but also this filler material is critical for the mechanical and thermal performance of those potting materials, of those self-leveling materials. If you lose them somewhere in the equipment, it can happen that your final product differs from the specification in terms of the mechanical or thermal performance. So also, as you can, okay, yeah, we can jump to the next one. What is the conclusion for those self-leveling materials? What do you have to do in automatic equipment? It's very important that you do a continuous material movement with a moderately high or flow velocity. That means you have to agitate those materials, which you can see on the right-hand side in the picture. You have to thoroughly agitate everything. You don't have avoid any shadow zones in the vessel or in the container. And second, it's very important that you recirculate the material. As you can see it on the right on the picture on the right-hand side, we transport the material from the feed pump, which is directly underneath the vessel, into a hosing system which feeds the material directly to the dispensing pump. And we feed more material to the dispensing pump that we need, that we have a constant flow of material. But that material, what gets consumed by the dispensing pump, gets injected into parts, but most of the material gets transported back to the tank itself, so that you have a closed loop, that you have in the complete system, that you have a movement of the material, that this mechanism of sedimentation is avoided. On the next slide, I want to talk a little bit more about the non-self-leveling materials, especially talking about the thermal interface materials, what Till already presented. Those thermal interface materials, they are particularly sensitive in terms of the loss of polymer matrix. Remember, I said that the filler level of those materials, they go up to round about 80% or even more plain filler, which is a solid. So a loss of a tiny bit of polymer matrix could jeopardize the flowability and could drastically influence the rheological properties of such materials. So what is a complete showstopper for such materials when you have in your hosing and piping, when there are leakage in a way that you have joints and sealing elements which are not completely dense towards the transport of the polymer matrix. Such materials normally, a very prominent chemistry class for such materials is silicon. So silicon as the polymer matrix for thermal interface materials. And those silicons, they have tendency to creep through every tiny insecured joints and sealing elements. And what will happen when you have such a leakage, such a small leakage? First, you lose a little bit of polymer, which is presented on the left side of the picture, and this polymer transports through the joint, and the filler with the filler particles are too large that and cannot pass that small cavity. Resulting in the formation of such a plug which is in close proximity to the leakage area. What happens next is that the vector of speed in that area slows down, and more and more, and since more and more polymer is lost, more and more of this solid filler material gets stuck in that area up to a situation where the hose is completely blocked, which causes, of course, a stop in production and a rework of that position by unscrewing it, removing the material, purging processes, and so on. Could be a downtime of several hours when such things happen. So this has to be avoided. On the next slide, you see a different spoilage mechanism, special and known for thermal interface materials. And this is found in close proximity to the material feed system. I brought along a small picture which you can see on the left-hand side. This is a pail preparation system for 200-liter bins for a thermal interface material for battery thermal management, for example, where high volumes are required. And what you have is you have a kind of a following plate which sits directly on original container of your material supplier, and there's a tiny sealing element around. And if this sealing element is not properly aligned with the even wall of the container, or there's a small welding on the drum, it can happen that you lose polymer matrix over time. And that brings you in the situation that you form a certain cake underneath the following plate, and which grows over time, and can bring you in a situation that at a certain point when that cake is formed, that you can't pump that material anymore out of your container. That risks that are two major risks. One is the risk that your production is stopped due to this issue, and the second is, of course, the rest of the pail is unprocessable. That means that would be something for the garbage, and that would be costly, of course. Another thing is that when you lose polymer matrix, you change, of course, the final product on your the final properties of your thermal interface material on your product. That means you get a reduced wet adhesion that could jeopardize the application process. I think Till will show us later on some pictures of it. I don't know. Is there a question? Someone raised their hand. Maybe we answer them at the end.
Yeah, yes, we'll address the questions at the end in the Q&A session, Jan. Thank you.
Okay, perfect. Okay, so on the next slide, oh, this is the previous one. I will highlight a little bit of that what Till already mentioned, that those materials, they have a tendency of sedimentation. And they are intrinsically sensitive for separation effects. Why is that so? Remember, those materials have a very high filler level. And in order to get those materials stable, the formulation consists not only out of that polymer matrix, but also there are certain additives in it, like wetting reagents. Those wetting reagents, they cover the surface of the filler particles, that they have a certain interconnection with the polymer matrix to get a stable formulation over time. And this is like a sensitive, those materials, they form a sensitive equilibrium. That means over time, they have a tendency to form a gradient in the original container. That is one aspect, which we will see later on our results. The second aspect is that they have a tendency to de-aggregate, to separate under shear stress or high pressure feed in such systems. So this is also something what we have to address in a way when we want to process those materials in an industrial environment. Okay. On the next slide, I will sum a bit the pathways. We have various mechanisms for material spoilage in those 2K adhesives. I highlighted the self-leveling materials or thermal interface materials, which are the most pronounced or most prominent material classes for such problems. One is the sedimentation effect, that filler particles start over time to sediment in low flow areas and causing blockages or inconsistencies in the formulation itself later in the final product. We have the polymer matrix loss that means leakage of polymer matrix on seals or in close proximity to the following plate. And we have that intrinsic instability, which leads us to a gradient in the original containers, and of course the sensitivity towards high shear stress and high feed pressures. That's the end of my part of the presentation. I have some conclusion to tell. Okay, what are the key strategies to rule those things out? For the sedimentation effect, avoid low flow or shadow zones in material handling systems. That's very important. Ensure a constant material movement with medium to high speed vector. And especially for the thermal interface materials, minimize transport pressure and transport shear stress. Especially when the system is idle, don't put too much pressure on the original bins that you don't lose any polymer matrix. Very important is monitor and secure all sealing points in such a machine, and control the feed pressure to maintain the material stability. That means you need to pump the material under pressure. Of course, it's not, otherwise it's not feasible to process those materials. However, keep the pressure on those materials as low as possible, and when monitor the pressure on several points in the dispensing and metering system. On a very important aspect is also monitor the metering of the dispensing pump over time. That's the end of my part now. And I will pass over to Brandon, who will present our results, what we had at Forvia along with Till. And I'm happy to see what he will show us now. Thank you.
Thanks, Jan. As Adam already introduced me, I'm Brandon Brown, VP of Engineering at C-Therm. And first, I'd like to give you a bit of an orientation on how the MTPS sensor operates. The MTPS sensor is a non-destructive technology. It was first developed for process monitoring and powder manufacturing, such as pharmaceutical industries and metal injection feedstock. The patented guard ring, it forces the heat flow to be in one direction. The sensor coil provides the main heat pulse into the sample and is simultaneously monitored as the temperature progresses. Generally, the slope of the temperature over the square root of time will quantify a sample's effusivity. Samples with high effusivity, such as metals, will show a lower temperature slope, while something like a foam will show a higher temperature slope. This is very similar to actually touching materials. Like just looking at my desk here, if I touch a plastic pen and my metal water bottle, the metal object will obviously feel cooler, and this is actually the effect of thermal effusivity. Next slide. Taking a look at the anatomy of the MTPS sensor, the sensor is made of stainless steel, which provides durability, resistance to various environmental conditions, and broad chemical compatibility. The sensor chiplet uses interfacial thermal reflectance to its advantage, helping it measure a wide range of materials, everything from aerogels to metals and everything in between. Importantly, the chip itself was also designed to be chemically stable, since us engineers and scientists seem to like to make products that are not always friendly to many types of sensors. Next slide. Previously, most of our work in the filled polymers domain has been in formulation development and checking filler dispersion during the R&D or qualification phases. The biggest challenge the composite folks have in formulation of conductive fillers is getting the distribution right, and then taking something that was done in a lab environment and bringing it to the production floor. If you know heat capacity and density of a sample, I think Adam talked about this earlier, it's possible to calculate thermal conductivity from effusivity, which in this case was the goal of this application, but we also have calibrations for many material classes. Here, the sample, you can visually see the areas of high and low concentration of conductive filler. These are the black areas, are the high concentration. When we measured the sample over a grid pattern, the correlation between the high filler concentration and the high thermal conductivity is clear, and this is a good example of bad filler dispersion. Next slide, please. From top to bottom, this is actually a similar problem. Hopefully you can see that there's a slight gradient through this sample. You can see it better on a bright monitor, I suppose, but there's a gradient between top and bottom of this sample. If you were to measure the sample using a steady state method, you would only measure the average through the sample. And this is exactly what happened to a client of ours. We had one client who had two groups within the same organization, the R&D and the production teams, where the R&D group was telling the production team the QC samples were passing, and the production team was telling the R&D group that they were seeing material failures. The root cause was later determined to be that settling had occurred, which was only possible to see using our MTPS single-sided transient technique, where we measured each side separately. And in this case, you can see there's an order of magnitude difference in performance just due to settling during curing. Next slide, please. One more example before I get into the results. This was testing done, we performed for HB Fuller, where they wanted to obtain insight into the thermal performance of their adhesives into both cured and uncured states. In this case, these adhesives would then be used in EV battery packs. There are many methods that can measure fully cured samples because the samples are quite stable. You can make the sample, cure it, easy peasy. However, uncured, you want to have very quick data acquisition. It's very important if you're trying to measure something before the curing process occurs. We've generally seen an upward shift in thermal conductivity in many of the adhesives that we've tested as they cured in the past, and this was also the result found here. Next slide, please. Process monitoring integration, right. So with all that background, we can now start to think about integration locations. Here's a bit of a line art rendition of a two-part dispensing machine with all the safety barriers removed. In essence, you have two barrel preparation systems and a dispensing head. On each barrel preparation systems, there's 3 general locations that we're monitoring, that we're testing on the following plate, near the pump, and after the pump along the material transport hose. The final potential location you could monitor the material is right at the dispensing head, right near the mixer. In partnership with bdtronic over the past few years, we've experimented with a lot of these locations. Next slide, please. Yeah, here we can actually see one of the prototype sensors we've used and a picture of the following plate that we'd integrated it to. Over the span of the study, we tested 2 locations on the following plate, generally just testing different radiuses along the following plate. Next slide. And sometimes science is fun. Here's Jan and I having a Breaking Bad moment in one of bdtronic's lab research spaces. Yeah. One of the big benefits to measuring on the following plate is that the pressure was very near ambient in the bdtronic equipment, and we're able to get good reading on the top layer. However, not all the material passed over the one spot on the top plate, and this is because if you're measuring an area and you're measuring here, the material on this side doesn't flow over it. So the locations we tested, so another location we tested with great success was just at a valve, right just below the pump. This again had the benefit of being at near ambient pressure conditions, but also had all the material to be processed would be passing through this point. So anyone can measure something good and get good results, but we wanted to make sure that we can measure bad things. So the results of the measurements here are the smoking gun we'd been hoping for. Here the buckets we've been testing were purposely expired. Yeah, so testing a bad material and getting bad results in this case was a good thing. It means that we can detect good versus bad. If I recall correctly, these barrels were donated to us after not being stored in accordance with the manufacturer's directions, and it was also well past the expiry date. The results shown here after testing parts A and B, or after testing parts A and B sequentially, because that's how our experiment was configured, but you could easily do it in parallel as well, simultaneously. The first thing I want to point out to you is that there's a red line on here indicating 3 watts per meter Kelvin specification after it was converted to effusivity using the heat capacity and density information given on the technical data sheet. Given how poorly this barrel was handled, it was interesting to see that the formulation was stable beyond the first 15% of part B and maybe the first 3% of part A. Again, based on our experience, we'd expect the thermal performance to increase as the material cures. So this is the material as it's being transported through the pipe in an uncured state. On a following slide, I've got a picture of one of the barrels, but here, stay on the slide, please. But the data clearly shows that both parts suffered from settling, where the top layer consisted of insulating silicone oil. And right at the end of the barrel, right at 0%, you can see that this is where the sensor was starting to see the cake that had formed. So with proper monitoring, it could be possible to bleed off the top and use the middle portion of the barrel, which is still good. And since this is a 200-liter barrel, the material cost could be, for example, over $10,000 per barrel. And so there's a great potential for savings here. Next slide. And this is just an example of one of the bad barrels. Here, it's a very spoiled barrel. You can clearly see the sheen of oil on top. And had this oil been processed in a live environment, it may have caused a failure later in the production, as you'd get like a bubble of very poorly performing material moving through the equipment. Next slide. So just a quick summary of some of our initial testing here. This was like over the course of, I think, 2 years. We also tested to see if the material moving across the sensor had any effect. And so this was basically to show that static testing with the pump stopped versus dynamic testing, like with the pump running, demonstrated it had a negligible 3% bias during normal operation, and even increasing the pump speed to 20%, which I believe was the maximum nominal operating speed for some of this equipment. It only showed a further 1% bias in the results. During the good or stable middle section, the material generally tested between 2,800 to 3,200 effusivity units, which is roughly equivalent to a thermal conductivity of above 3.5 watts per meter Kelvin, which is better than the 3 watt per meter Kelvin specification. Next slide, please. So now we'd established that the sensor can detect inconsistencies in the material's thermal performance during processing. bdtronic reached out to HELLA Forvia and pitched the idea of running the study in a live production environment. Moving this forward, Jan and his team at bdtronic created a custom adapter block to integrate the sensor in the hose above the pump, and you can see it installed here. You can also see the control box we've mounted nearby. The sensor was situated in the pipe, in a pipe where all the material processed from the bucket would pass through. During some of the initial testing after installation, we checked again and we saw we were able to successfully measure the material's effusivity without slowing down or requiring a stop of the pump, established pump speeds required on this production line, which was super important because we weren't allowed to stop production. That said, the material flow rate was relatively low. I believe it was something in like a small number of grams per minute. Next slide, please. Yeah, so here we see the sensor, some modifications for this specific implementation. Yeah, at this new location, the first concern was that it was required to withstand a one-sided pressure of 12 bar, or about 175 psi for us North Americans. It took some thinking to get past a few of the devilish details, but we ended up finding a solution. The sensor was also modified so it could easily be inserted and removed from the adapter blocks, and a gasket was used to make sure there's no leakage. During all of these studies that we've been doing, we've been concerned with and monitoring sensor abrasion. There's some after-action pictures later, but the abrasive nature of the filled adhesive really shouldn't be understated here. So next slide, please. So finally, data. Okay, so here's this is the first trial of the installed in one of the production lines with filled adhesive, very similar to the expired bucket that we had later, but this is not expired, obviously. Here, and this was collected with Till and his group at HELLA Forvia. This is just one run. Many of the runs of this #1 sample looked similar. Again, the cured specification line is shown. Yeah, converted using the heat capacity and density from the TDS. The filled adhesive here is what I'd be considered very well behaved, and I suspect it's also priced appropriately. Again, from what we've seen in the past, as a material cures, the effusivity and conductivity would increase after curing, meaning the material shown here would still outperform the specification. And this is great news for Till and his team. Next slide, please. So moving to another production line and another filled adhesive, I've overlaid a number of pails here which were processed to show the variance of the second filled adhesive. It had some different properties, different viscosities. Again, this was mounted above the pump in a pipe where all the material processed from their pail would flow through. So here, the red line represents a nominal value. There wasn't enough information in the data sheet to directly calculate the effusivity, but for the purposes of this testing, we were focusing on consistency anyway, so the nominal value was used. I've highlighted 3 distinct zones here, zones of performance. From left to right, we have the start of a new bucket, which may be getting a bit of mixture from the end of the previous bucket as the material moves through the pump and the pipe. The middle, we have a zone of stability spanning about 80% of the pail, and finally at the end of the pail, where the filler would have settled to, you can see a slight increase in effusivity. All of these pails perform quite well, but right at the start of one of the pails, which I believe is pail 5, you can see there's an off nominal dip in effusivity. So let's investigate on the next slide. Yep. So zooming in, so this is just at the end of pail 4 and just at the start of pail 5. Here it's shown instead of like as a fill, pail fill, the x-axis now represents time as it was processed. And so you can see how it relates pail 4 and pail 5. And it appears that right at the start of pail 5, there's just over a 10% dip off nominal. And you can still see the increase in effusivity at the end. And based on what we've seen from a few slides ago, I suspect this pail may have suffered from some settling and may have had a small oily layer, silicone oily layer on top. Next slide. Yeah, just to give a bit more insight into the adhesives, you know, Jan has done a really good job. For those of you who've never used this type of filled adhesive before, you can think of it as like a toothpaste. If that toothpaste was mixed with ceramic dust, it's very thick and gritty. The data we're gathering, so after we'd gathered all the data and everything was completed, the sensor was removed, you know, inspected, and we haven't seen any abrasion from our tests in any of our testing over the years. And one of the theory that we had was the material was moving slowly through past our sensor slowly enough that any of the abrasive materials actually rolled over the surface instead of ablating it or abrading it. But the end of it is that we didn't see any sensor abrasion, and Till's got some microscopic pictures in his section later on. Actually, it's back to Till. So yeah, take it away, Till.
Thank you, Brandon. Okay, so yeah, Brandon and Jan gave a lot of information. So yeah, I would just continue with the test summary from production side. So the sensor delivered a stable performance under real harsh series conditions. It shows a pressure stability at least over 10 bars. So this was the pressure adapted to the system due to the normal processing. We have no wear and tear on the sensor surfaces as Brandon already told. So on the right side, you can see the sensor surface after our testing period in different magnifications. So the upper one is a 20-time magnification, and below you see a 200-time magnification. And there are really no scratches seeable. We got reliable measuring results at 2 different dosing setups, so means 2 different dosing speeds and flow speeds of the material through the sensor surface, as well as 2 different materials. We have an easy and plug-and-play installation due to the retrofit adapter, and we got a confirmation of the theoretical material behavior inside the material system because you couldn't look inside for sure. Next slide, please. Yeah, and this brings me to the potential benefit for production as well as the real failure pictures to just bring the theoretical behaviors and challenges of these materials into reality. So an earlier as possible inline detection of a filler content change brings us really potential benefits of, for example, the reduction of downtime, so technical availability increase for all those of you who works in production. Yeah, due to the elimination of system flushing. So normally we could only see it as on the left upper picture that a higher filler content leads, for example, to a reduced wet adhesion on a metal surface. In this case, for sure, you could detect the filler change, but then the material is already processed, and this means the complete system is full, so the complete system from the preparation system to the dosing head is full of not good material or material with a higher filler content in this case, yeah, it's sometimes as well already produced, and yeah, this means you have to flush the complete system, which normally needs around about 1.5 hour per event. This depends for sure on the setup of your machine, on the length of your material pipes or tubes. You have a reduction of material waste, or could have a reduction of material waste due to the dried out material, so you do not have to flush the whole system. If you directly measure the filler content change behind your feeding pump, you could just put the bucket off, use a new bucket, and within the tubes and the upmixing of the material inside the tubes due to the flow, you don't have to waste some material, and for sure you even need not 1.5 hour per event. You need at least 10 minutes around roundabout. Then we have the reduction of the reduced scrap for sure, as I already told, with the wet adhesion, which could lead to NOK parts in production. And we have a reduced wear and tear due to the early detection before the material goes through the dosing pumps. And within the years, we made some calculations and analysis, and this is up to 1/6 of an overall lifetime if you have a bucket with really high filler content. With that, I would hand over to Adam for just some more words.
That's great. Thank you very much. We'll try to bring this to a close here pretty efficiently, where we're going a little bit over time, but really great, I think, information to share with the audience here. And I want to just extend my appreciation and thanks to Till, to Jan, and to Brandon. Wonderful job on this, and I think very, very interesting content for the industry. If you're reviewing this and interested, hey, how could we try something similar? Please reach out to us either through the chat box, or you can message us in response to our follow-up email. We're happy to discuss an on-site trial. There's a quick little survey here you can fill in, and that will also help us track that. If you would be interested in exploring an on-site trial, there are some costs to that. But it is certainly something we can present to you if that's something that's of interest. This work is going to be summarized in a white paper that is going to be made available next week. If you registered for this event, that new publication will be coming out next week. It's just going through some final editorial review. So please feel free to, well, keep an eye out for that, I would say. If you have colleagues who didn't register for this event, but you think would be interested, it will be available on our website if they would like to check it out. Of course, we can reach out to them directly as well. But if you want to make sure you receive it, just please hit the yes button on the poll, and we'll be sure to follow up with you accordingly. Our website does have a range of other resources available. All of these webinars are recorded and available on the website, as are a number of different technical publications. We also cross-link to other publications, so we can direct you to other sites where you can buy some of the publications that reference this technology, or we have our own internal application notes. Those are freely available for download. It's a rich resource. We put a lot of effort into it. Please feel free to make use of it. It's a free resource to you if you're interested in these areas. Just a couple other housekeeping items as we close out and move to the Q&A. We have a number of upcoming webinars in May, June, July. A little bit later this month, we'll be looking at bio-based composites. If you're interested in bio-based composites, we'll be looking at the thermal conductivity measurement of them. We'll feature some other test methods as well besides MTPS. If you're into textiles, we'll highlight a little bit of our work with leading brands in the textile space around quantifying warm feel or cool touch and how that impacts product performance in the textile field. Probably most interesting to this audience, we are going to be presenting a webinar with ZFW, who is, I think, the leaders in the field when it comes to TIM testers, based out of Stuttgart. They have a very impressive portfolio of TIM testers. They're also introducing some vibration mechanisms in some of that analysis as well, which I think is really cool and interesting. So stay tuned for that. That date is not fully locked, but if you're interested in that one, you can register through the link, and we'll save you a spot for that event. It should be a very popular one. We're going to feature other methods for TIMs as well, looking at the ISO standard for measuring TIMs based on the TPS method. We'll also delve into a little bit deeper some of the MTPS work. My last real plug here is on the, if you're interested in a technical consultation, you'd like a quote, you're interested in testing services, these can all be done through the chat box if you want to enter anything there. Do follow us on LinkedIn. This is our primary mechanism for sharing information. And lastly, let me just thank you, the audience. We did go a little bit over time on this one, but we didn't want to be too strict on the time. We knew there was a lot of really good information and content here to share with you. So we hope you found that interesting and valuable.